Hello, everyone. Welcome to the YugabyteDB Friday Tech Talks series. And I'm Kannan Muthukkaruppan, a co-founder at Yugabyte, and a pleasure to welcome you all. Today, I have with me one of the early engineers at Yugabyte, Timur Yusupov. So my pleasure to welcome him. And Timur, it would be great if you can introduce yourself, maybe just give a glimpse of the kind of things that you work on, as well as then introduce the topic and get started. Thank you, Timur.
Sure. Hello, everyone. My name is Timur. I'm software engineer at Yugabyte in distributed storage and transactions team. I'm working here for several years and mostly on different distributed document store layer components. For example, Bloom filters, Delta encoding, and some improvements in RPC layer to deal with network partitions and so on. And the latest, biggest project I was working on is automatic tablet splitting, which we will talk about today.
And early on, you worked on both sharding our Bloom filters as well as the indexes from being for large SSTable files. Yeah, a lot of
partitioning indexes. Right.
Yeah, a lot of fun projects. Yeah, go ahead, Timur.
Yeah. So before we talk about automatic tablet splitting, we will recall how YugabyteDB stores data, what is the tablet, how sharding works in YugabyteDB. Then we will see into which problems we may run into with fixed set of tablets. And after that, we will discover how actually automatic tablet splitting works and resolves these problems. And finally, we will see that in real cluster. So what is the tablet? In YugabyteDB, each user table is split into multiple tablets, and each tablet is just a group of rows. And table rows are grouped into tablets based on primary key, and for that we have two types of sharding, hash-based sharding and range-based sharding. In case of range-based sharding, each tablet is just a group of rows belonging to some range of primary key space. And for hash-based sharding, each tablet is a group of rows for which the hash function, our primary key, belongs to some range. And in this picture, you can see an example of a table which is split based on the hash, our primary key, into 3 tablets. So why do we need tablets? YugabyteDB is a distributed database which is running on multiple nodes. And we need to distribute the data and the load across all these nodes. So this is what we need tablets for. Also, for fault tolerance, each tablet has an replicas, which is free by default. And these replicas, which we also call tablet peers, and you can see them on picture, form a group which is used for data replication between these replicas, and which is done using rough consensus algorithm. When a table is created, we pre-split it into a number of tablets specified by the user or automatically to have a fixed number of tablets per node. For example, on this slide, you can see that the user table has been split into 16 tablets, which results total in 48 tablet peers distributed across 4 nodes, 12 tablet peers or replicas per each node. And also you can look at docsyugabyte.com site in architecture section and learn more details about that, as well as refer to one of the first episodes, I think it's episode 3 of YFTT, about sharding in details. So which problems we can have with a fixed set of tablets? First, we need to think how to pre-split table in advance. And there is no universal solution for that, especially for range sharding, or we need to rely on default pre-splitting, which also doesn't solve all the problems if we keep a set of tablets fixed during the whole life of the table. Another thing is that we have tables that are growing too large. To support the workload, we need to continuously add nodes to the cluster. And we may reach a scenario where the number of nodes or disks exceed number of tablets, and we might be using not the whole cluster capacity in terms of CPU or disks. And this requires to split existing tablets and effectively rebalance the cluster. Also, there might be
Yeah, I think these points are worth just emphasizing, like you said, Timur. One, I think you mentioned is even if you can pre-split, let's say you pre-split a table into 20 tablets, but at some point, maybe your cluster became big enough, you're running on a 40 node cluster or a 50 node cluster, then 20 tablets isn't sufficient. So while pre-splitting helps, but you do need dynamic further automatic splitting, which is what you're going to cover in this talk. So that was one use case you mentioned. The other you pointed out was if the primary key, if the user wants like range sharding, meaning they want their primary key not to be hash organized but ascending organized or descending organized. You mentioned like it is hard to pre-split in advance because the system, and maybe it's worth mentioning why that is the case, because the system, suppose your primary key column is a text column, and maybe you plan to store email addresses in it. The system doesn't know ahead of time what an ideal split point is. What is the domain of this text column? Are there going to be more email addresses starting with A or B or C? It may be very, very dependent on the population of that particular data set. So there are many reasons where pre-splitting is not sufficient, and you need this automatic tablet splitting capability.
Yeah, and another use case is a hard chart issue when workload is mostly accessing some specific range of primary keys, and that can reside in a single tablet. And in this case, we can distribute the load by splitting this tablet into multiple tablets and again rebalancing them across the cluster. Right. So in YugabyteDB, we implemented automatic splitting of tablets to resolve these issues, and let's see how it works. So when automated tablet splitting is enabled, each table is created with just a single tablet per cluster for range sharding, because as we discussed earlier, we cannot know in advance which particular ranges will be used by the user workload. And in case of hash sharding, we created with one tablet per node because we can distribute all the hash space across the whole cluster, just having one tablet per node and utilizing all the nodes. And then the system starts monitoring on disk size of each tablet. And as soon as some tablet reaches 512 megabytes, we split it into two halves of approximately the same size, and these new tablets replace the original tablet. And this flow phase is quite aggressive because of low threshold, and the idea is to split original tablet to distribute the load over the nodes and disks, and we complete the low phase as soon as we reach 8 tablets per node, because there is no benefit in having too many small tablets per node. Then tablets will grow until some of them reach 10 gigabytes. And the goal here is to be less aggressive because distribution is already correct, but we still want to keep tablets under reasonable size. So it is easier to rebalance the cluster when we will add new nodes. And this continues until we reach 24 tablets per node. Again, to prevent cluster from having too many tablets, because each tablet consumes CPU and memory resources as an overhead. But if, for example, some tablets reach 100 gigabytes, we also don't want tablets to be such to have a very big size, over 100 gigabytes, and because of that, we have a global threshold. After that, we will again start to split tablets to not have a bigger size, and then we have a final limit of having 256 tablets per table, again to not have too many tablets. And all these limits and thresholds are configurable and listed on the next slides.
So maybe before you go to the next slide, Timur, so yeah, maybe you could talk about what are the pros and cons of having, like too few tablets versus too many tablets? Like what, like why not keep splitting always when something is 512 MB? Why do we have a higher phase threshold? Maybe you could try to give that intuition. Suppose we didn't have a high phase threshold, right? And suppose we always split whenever a tablet reaches 512 MB.
Yeah, then we will end up with too
maybe
many.
what is the disadvantage of that? Like, maybe you could talk through some of that.
Yeah, then we will have too many tablets, and each tablet occupies additional memory resources and uses additional CPU for raft work. So we will just be using more resources than needed to serve the user workload.
Exactly. The raft overhead and other processing overhead of every tablet is basically unnecessary, and there's a point of diminishing returns where beyond a certain number of tablets you don't get that much advantage. So that makes sense. I'll keep going for the next slide.
Okay, so here I listed that we have a number of flags to configure automated tablet splitting thresholds and limits. And besides that, we also have some additional flags that are listed by the link below. I just wanted to mention two flags here. Split operation by itself is very fast because data files for new tablets are created just as a hard links on the same disk, and we add metadata to each new tablet to take into account only their respective key ranges. But after that, after we created these tablets, the load on the node is temporarily increased by starting a background compaction job to remove non-relevant keys from these new tablets. And we can use these additional flags to limit tablet splitting concurrency and limit this additional intermediate load on the system just by setting how many tablets we can split per server or globally per cluster concurrency. And by default, these settings are pretty conservative. It's just set to 1 for each of these flags. And this should be enough for most use cases.
Timur, one question on the previous slide, like for example, when we say we stay in this low threshold till we get about 8 tablets per node, is it 8 tablets including the replication factor, or 8 tablets not including the replication factor? Meaning if RF is 3, then is it fair to say roughly is it like going to be actually 24 tablets per node, or is it 8 tablets per node?
I think it should be 8 tablets per node.
Okay, so this includes some tablets could be leaders and some tablets could be followers. So you're saying it includes it includes the replication factor. It's not got it. Thank you.
Okay, so finally we can switch to the demo and see how it works in practice. So I have a pre-running cluster, internal cluster with the 3 nodes. And let's just go to the master UI and see. Okay, I need to re-authenticate. Okay, so here at the master UI, we can see a list of tables. And there are no currently any user tables, so I will create one. I need a terminal for this.
And maybe just slightly bigger font if you can. Okay, yeah.
Okay, so I will create a table which has exactly two columns. One is ID, which will be serially generated and unique, and another one is text column, and it will use range sharding. So let's check that this table was created. Okay, and now we can click on the table name and see a list of tablets. Okay, here we can see that there is just a single tablet per cluster, and it covers the whole primary key range. Then we can insert 200 megabytes of data into this table using copy from program YSQL statement. So it basically uses random generated data and encodes it is a base 64 split into blocks of 16 kilobytes per row, and we only write 200 megabytes of data. We can check.
That's a neat single line to load
Yeah.
some synthetic data.
Very useful thing. So as we can see, IDs are increased monotonically, and length of each data value is exactly 16 kilobytes. Also, we can make sure that all the data loaded is about 200 megabytes. And
Nice.
let's see in master UI what we will have in the tablet. So in tablet, we have SSD files of 200 megabytes. This is still under low threshold, so we need to add more data. Let's add another 200 megabytes.
Normally, because of compression, the size would be smaller on disk, but because you're loading random data, you're not getting any compression, which makes sense.
Yeah. So now we have 400 megabytes, which is still under threshold. Let's add another 200. Okay.
And because our the low phase trigger is at 512 megabytes, that's why nothing quite happened when you got to 400 MB, correct?
Yeah. And now we can see that original tablet reaches 600 megabytes. And after that, it was split into two new tablets that have split depth 1, and they cover respective halves of the original primary key space. And if we refresh, we can see that, okay, and there was another split, because first split was not actually in two halves, but into 500 megabytes and about 100 megabytes. So it did another split. And now we have four tablets of, now we have three running tablets, which covers the original primary key space. And we see that original tablet has been already deleted because it has been fully split on all replicas. And if we refresh the UI, we can see that one of level 1 tablets, which was replaced by two second level tablets, has been already deleted after it was fully split. So now we have three tablets covering the whole primary key space.
So if you look at that second column for on the first row, like looks like we also display the key range itself. So in your case, was it an integer key? And this now this tablet is going to cover the 16K to about 32K range of that integer space. Is that how to interpret?
Yeah. The primary key is integer ID, and now this tablet will cover from 16K to 32K values. Another one will cover from the beginning, which is minus minimum value for the int until 16K, and another one will cover from 32K till the end.
And although right now the cluster hasn't changed in size, but the reason to keep all these tablets in some in some manageable sizes, because when you add a new node, then these are the parts that easily move around in the system and help the system keep it balanced and reshard it automatically, if you will, right?
Yeah. Also, we can see that the load balancer already distributed the ledgers of this tablet across different nodes, so the load will be already distributed more evenly across the cluster.
Yeah, that's a good point, Timur. So it was a 3-node cluster, replication factor 3. So already all the nodes had all the data, but because we were in a one tablet state to begin with, there was only one leader. So it was a little bit unbalanced in that sense. Whereas now that we have more tablets, different nodes are taking up the responsibility of being the leader for different shards of the different ranges. Yeah, that makes sense.
Yeah. And all this happens transparently for the client application. So as we saw, there was no errors or issues in client side while we were loading with 600 megabytes. So all this tablet splitting happens transparently for the user.
And basically internally there are, if as part of that giant copy command, if internally a tablet was caught moving, we have the right retries and mechanisms in place. That's why we're not seeing the errors, any errors at the application layer.
Yeah. All tablet splitting related mechanics is handled internally and transparently for the user. Also, I have another example of universe I had running today for few hours. So it started with one tablet, and it was 9-node universe. So it will take some time to load.
What you're seeing is the control plane side of Yugabyte. This is our internal portal, which is managing about 100 plus Yugabyte universes, if I'm not mistaken.
Yeah. So it was a YSQL workload which started with just one tablet, and we see that throughput was about 8K inserts per second, and CPU usage was about 12%. And we can also look at the tablet splitting metrics. Okay, so this spikes demonstrates that there were tablet splitting operations happening. So first the operation is added to the tablet, then it is applied and tablet is actually split. And after that, post-split compaction is happening for the new tablets. So all of this is demonstrated here. And we see that around the same time, tablets were split. We had an increase in throughput because we now can utilize more nodes in the cluster to support running workload, and CPU usage was increasing as soon as we utilize new nodes. And that demonstrates the benefit of tablet splitting to utilize the whole cluster.
Got it. Because you had a 9-node cluster, but to begin with, it was a single tablet, so and replication factor 3, so only 3 nodes were getting utilized, right? And then in the low phase threshold, we aggressively start splitting as the tablets reach 512 MB size. So pretty soon the system is automatically starting not only splitting, but it is also starting, the load balancer is also starting to move those tablets around to the remaining 6 nodes. And everything is just happening automatically, right? Yeah. By the way, I was not aware of those metrics. So I learned something new, like the metrics that you showed about tablet splitting. I didn't realize we had already added it to the Yugabyte Anywhere control plane also. So that was cool.
Yeah, this is very useful. I think that's it for the demo.
So maybe just it might be because you kind of covered that point quickly. Maybe just if you could explain the mechanics of what exactly happens behind the scenes when let's say I have a tablet with a 100 gigabyte or I don't know, it doesn't have to be 100 gigabyte, 10 gigabyte SS table file behind the scenes. What exactly happens when you decide this tablet is going to be split?
Okay, so at master side, we registered 2 new tablets to eventually replace the original tablet. Then we apply a split raft operation to the tablet leader of the original tablet. And when we apply this operation, we hard link original SST files of the original tablet into 2 new directories, which will be used as the data directories for RocksDB of 2 new tablets. And because of that, it is very fast operation. We just need to update some fields in metadata to note for these new tablets that we will use only respective halves of the whole data of the original tablet. And we store lower bound key and upper bound key to filter this data. And after that, these tablets, as they form their own rough groups, are quickly elect their own leaders. And we use hinted leader election to make this faster, to not wait for failed leader. And after that,
so basically what you're saying is after this very quick operation, which is essentially like creating a thin clone by still pointing to the parent SS table files, but the metadata tells you, hey, this is the only half you're responsible for, this is the only half you're responsible for. So it's a very thin clone operation, but the system is now going to run for a little bit of time in this mode. But presumably now we need to delink our dependency on this parent SS table file so that this tablet is free to move around. So maybe, what happens next?
Yeah, what happens next? So we have fully operational new child tablets, and we schedule post-split full compaction that will remove keys that are not related to this key bounds of each tablet. And after that, all data will be read and processed through the compaction algorithm. And after that, each tablet will have on disk data only for its key range.
Makes sense. And I think you mentioned there are hopefully the default knobs already rate limit the number of compactions that are happening on behalf of splits. And maybe it's possible to tweak those to go more aggressive or less aggressive.
Yeah, this flux, which I was showing, which limits the number of concurrent split operations, this actually limits not only this fast split operation, but it also took into account post-split compaction phase. So we limit the whole cycle of the splitting, not just split operation itself.
Great. Yeah. Thank you so much, Timur, for joining and explaining this this topic on how Yugabyte does automatic tablet splitting. And are these two approaches complementary? Like if a table was using pre-splitting, like maybe you have an older cluster where the table was had created a certain pre-configured number of splits, and even for range sharded tables, we allow users create table syntax to actually specify the split points, like they can say A to C and C to Z and so on. So assuming a table has been created that way, can it still then take benefit of automatic tablet splitting if some of the tablets get very large?
Yeah, if you change the flag to enable auto splitting to true, then it will enable auto splitting mechanism, and it will apply the same thresholds for low phase, high phase, and so on. And it will split again the tablets you already have in the system according to these rules.
Got it. So this can be taken advantage of by pre-existing tables also.
Right.
All right. Thank you everyone for joining today. for another episode of the YugabyteDB Friday Tech Talk. Next week, we will not be having the same because of Thanksgiving holiday that we'll be celebrating, but see you again in 2 weeks. And over to you, Timur, for closing comments.
Yeah, thank you everyone for the attention.
All right. Have a good rest of the day and weekend. Thank you.
Thanks. Have a good rest of the week.